This skill is building on the last one. We're still looking at half-life and we're looking at radioactive materials decaying over time, but this time we're going to introduce the decay constant and a shortcut for calculating our masses and times. In this question, we're told a scientist measures how americium-240 decays over time and plots a graph of mass against time provided. So we can see we've got mass of americium-240 on the y-axis and time in days on the x-axis. Our first question is to find what is the half-life of americium-240. We're going to answer this question exactly the same way as we did in the previous skill. We're using our graph and we're looking at our initial mass or radioactivity or whatever it may be. Our initial mass here was 30. And we want to see how long it takes for that to halve. So half of 30 is 15. So as we go from 30 grams to 15 grams, the time taken should be our half-life. So looking on our graph, that puts us at 2 days for our half-life of americium. Let's fill that in. Awesome, okay, so we figured out our half-life. Next question is to find the decay constant, which we're going to then use in our equation. Let's head to the reference sheet. This is our equation that relates the half-life and the decay constant. T half, our half-life, is 0.693 divided by lambda, which represents the decay constant. So our half-life, T half, is 0.693 divided by lambda, which is our decay constant. In this case, we have T half and we want to find lambda. So I'm going to rearrange this by multiplying by lambda on both sides so that it will get cancelled out on the right. And then I'm going to divide by T half on both sides so that we'll leave lambda on its own on the left, which is what we're trying to find. So that gives us lambda is 0.693 divided by the half-life. So we can go ahead and put our numbers. That's 0.693 divided by the half-life, which we already found is 2 days. So that gets us an answer for the decay constant of 0.346. And our units are per day because our half-life was in days and that's on the bottom of the fraction. So we can go ahead and fill that in our answer box up here. 0.346 per day. Awesome. So now we have our decay constant. We're going to use that to answer this question. We're going to figure out how long it will take for the mass of americium-240 to drop to 1.69 grams. Now, 1.69 isn't a perfect number where we can just take 30 and we can divide and divide and divide. We'll never get 1.69 because it's not an exact multiple of the half-lives. So that's where our new equation and the decay constant is going to come in. Here's our nuclear decay equation. And this equation is going to calculate the mass or activity of our sample at any time. It doesn't have to be exact multiples of the half-life, using that decay constant as a factor. So we're going to go ahead and use that now. Here's our equation. So let's go through and look at each of our variables. NT, that's going to be our mass or our activity or whatever it may be of our sample at time t. So that's at our kind of final time. So based on our question, we're trying to figure out how long it will take for the mass to drop to 1.69 grams. That's going to be our final mass. So that's 1.69 grams. Then we've got N0. That's our mass or activity or whatever it may be at time 0, our initial mass. In this question, we can see from our graph, it started at 30. So that's going to be 30 grams. Then we've got E to the power of negative the decay constant times the time. So our decay constant, that's something we've already calculated. We got 0.346 per day. And the time, that's what we want to find. We want to find how long it takes for the mass to drop to 1.69 grams. So T is our unknown variable. We're going to need to rearrange this equation to get T on its own. So I'm going to start by dividing by N0 on both sides. So that's going to cancel on the right. Then to get rid of e to the power of, I'm going to have to lose ln, the natural log. So I'm going to do ln of nt over n0 is going to be equal to ln of e to the power of negative lambda t. But ln is the inverse function of e to the power of. So those are going to cancel out. And we're going to have ln of nt over n0 is equal to negative lambda t. So I just need to divide by negative lambda on both sides of my equation to get t on its own. So there's my equation. It's t is ln, the natural logarithm of nt divided by n0, and that's all divided by negative lambda. So let's go ahead and put in our numbers. It's ln of nt, that's our mass at the end, which was 1.69 grams, divided by n0, that's our initial mass, which was 30 grams, divided by negative the decay constant, which was 0.346 per day. If we put all that in our calculator, we're going to get out a time of 8.31 days. So let's go ahead and fill that in to check if we got it right. Awesome. So in this question, you can see we had our half-life exactly the same as we did in the previous skill. We used it to find our decay constant, and then we used it in our radioactive decay equation to figure out how much time would pass to get to some value of our mass. And we can use this equation even if we don't have an exact number of half-lives that have passed, because our half-life here was 2 days and 8.31 days had passed, which is somewhere between 4 and 5 half-lives, but it's not exact. So we couldn't just use our halving method we used before. In that case, we have to use this equation. However, you can use this equation even if it is an exact halving situation. This equation will always work. Let's do one more question of this type. This one's about uranium-238, which has a half-life of 4.5 billion years. It's one of the isotopes that makes rocks slightly radioactive. A geologist determines that a rock contains 14.4 milligrams of uranium-238, and she wants to know what mass of uranium-238 will remain after 3.74 billion years have passed. So we're going to be using the same equations we used before, the half-life equation and the radioactive decay equation. So our first step is finding the decay constant, lambda, of uranium-238. So that's going to be using this equation over here. Once again, we need to find lambda, so we're going to multiply by lambda on both sides to cancel it on the right. We're going to divide by t half on both sides to cancel that out and leave lambda on its own. So we're doing lambda is 0.693 divided by t half, which is the half-life. So putting in our numbers, that's 0.693 divided by our half-life, which from the question was 4.5 billion years, which gets us an answer of 0.154, and our units are per billion years because our half-life was in billions of years, and that was on the bottom of our fraction. So we're going to go ahead and fill in that answer now. We got an answer of 0.154 billion years for our decay constant. Awesome. Next step is figuring out what mass of uranium-238 will remain, and that's after 3.74 billion years have passed. So let's go ahead and fill out our variables for our equation. The time that's passed is going to be 3.74 billion years. The decay constant we just calculated is 0.154 per billion years. And we know our initial mass in our rock sample is 14.4 milligrams. That's N0, that's our initial mass or activity or whatever it may be. And the thing we're trying to find is the final mass after that time has passed. So in this case, our equation is already arranged correctly for us. We just need to plug in our numbers. So we can do that now. NT, our final mass, is going to be N0, which was 14.4 milligrams, multiplied by e to the power of negative, the decay constant, which was 0.154, multiplied by the time, which was 3.74. If we put that all into our calculator, we're going to get a final mass of 8.10 milligrams. So let's go ahead and fill that in here. Awesome. So in this question, because we are finding the final mass, we didn't actually need to rearrange our equation. We could just plug our numbers in. Again, we found the decay constant using that equation for half-life. So you can see these questions work similarly to the previous skill, but now we're able to find the final mass or activity of a sample after any length of time has passed. It doesn't have to be an exact multiple of the number of half-lives because we're using this equation here.